In this screencast I'm going to use the residue theorem to evaluate the integral given here. That is the integral between minus infinity and plus infinity of t squared divided by t squared plus 4 all squared. And in order to do this I'm going to use contour integration. And let me just first of all write down the integrand, but as a function of a complex variable z. And what you should notice there is that this integrand, this function, is analytic everywhere except at the poles, that is the points where z squared plus 4 equals 0, which is where z equals plus or minus 2i. And those are poles of order 2 because of the squared outside the bracket. And so that leads me then to think about, I'm still ultimately wanting to evaluate that integral at the start, the integral in terms of t, but let me instead at the moment look at evaluating this contour integral, the integral around a contour gamma of my function of z with respect to z, where gamma is the sum of two separate contours, and I will show you what I mean here. If I sketch them, I'll have gamma 1 running along the real axis, so that eventually what I'm going to want to do is let little r tend to infinity, and then I will have the integral that I'm after, that I was given at the top. That's my gamma 1, and then for my gamma 2 I'm going to have a semicircle joining gamma 1 at either end. And what I want is for my poles to be either inside or outside this contour, this closed contour gamma. And so if I want to put 2i, for example, inside here, I just have to make sure I restrict little r to be greater than 2. Which I can certainly do because I'm going to want little r to tend to infinity eventually. So I can now use the residue theorem to evaluate this integral, because one of the poles is inside and therefore its residue will contribute to the integral, and the other pole is outside and so it won't contribute at all. The contour does not go through either of the poles. So let me now look at evaluating this integral, and what I will need to do is to work out the residue of my function at the point 2i. And in order to do that, what you have to remember is that the pole is of order 2 at this point, and we have a general result that if f has a pole of order k at a point alpha, then the residue of f at that point alpha is given by this result here. I'm not going to prove it, but you can look it up, I'm sure, and find it. It's 1 over k minus 1 factorial, the limit as z tends to alpha, and we basically want to remove the poles from the problem, from the workings, and so what we have here is the derivative to the k minus 1th order of z minus alpha to the k f of z. I'm just running out of space there, but I can just about do it. So that whole thing is differentiated. So if you've not seen that result before, you may want to stop the screencast and try and locate it somewhere, or at least if not, just think about how it works and where it's come from. I will now illustrate its use in this case. What we have is a pole of order 2. So here we have k equaling 2. We're wanting to evaluate the residue at 2i, and my f of z is disappeared off the top of the screencast, but it was z squared over z squared plus 4 all squared. So what I'm going to have is the residue of that f at the point 2i is in fact, and I'm now just applying this result, so it's 1 over k minus 1 factorial. I'm looking at this first bit here. Well, k is 2, so that's just 1 over 1, which is 1, so I can forget about that. It's the limit as z tends to 2I of, and again if k is 1, that's just the first derivative. And then what I have to do is multiply z minus 2I to the k times by the function. And here you can see the fact that this singularity is going to be removed, which is what we're after in order to evaluate this limit. Because I need to simplify what I'm differentiating before I differentiate it, and I hope you can see this term here is z minus 2I, z plus 2I, all squared. And so in fact what I end up with is z squared in the numerator, and the z minus 2i's will cancel, and I've just got z plus 2I all squared in the denominator. And that makes that limit very easy to evaluate. First of all, I actually have to do the differentiation, for which I will just use the quotient rule. Whoops. So if I'm differentiating u over v, it's v du minus u dv all over v squared. And I will leave you now to check that if you do now evaluate this in the limit as z tends to 2i, which just means in this case replacing z by 2i, if you evaluate it and simplify it, you should see that you end up with minus an eighth I. I'll leave you to check that, so do stop the screencast now if you need to. So just to remind you what we were doing here, I'll just go up to show you, we were actually evaluating this integral here around the closed contour gamma, which is the sum of the two individual gamma 1's and gamma 2's. So I'll just summarise that here. So I, which is the sum over the whole of gamma of my f of z, the integral of that dz, if you remember what that is, by the residue theorem it's 2 pi I multiplied by the sum of the residues of all the poles that are inside my contour. And so the only one I have inside is z equals 2i, and the residue of f at the point 2i is minus an eighth I. That's the result I've just found. So that now gives me my result. I squared is minus 1. So in fact, that integral around the whole closed contour is pi by 4. Again, you should stop the screencast at this stage if you are at all unsure, and just check that you're happy with what I've done so far. Basically what we've done, because I is the sum of two separate contours, is I have shown that that's the integral along gamma 1, and then I'm having to integrate along gamma 2, which was that semicircular path, and the total of that is the I, the integral that I've just found, which is pi by 4. So what the question, our actual question that I posed at the start, was this integral in the limit as r tends to infinity. And so what I now need to do is look at this second integral, the integral with gamma 2 in it, and check what that value is. It may tend to 0 as r tends to infinity, or it may have a value. We need to look at what that is, and then hopefully I can find the answer to the original problem posed. So let's now just look at this second integral. What I'm wanting to do is to evaluate this integral where gamma 2, if you remember, was the semicircular path from r to minus r, where r was greater than 2. And in fact I'm going to want r to tend to infinity, because that's what I want for my final problem. Now, in order to do this, first of all I'm going to look at the triangle inequality. And let's just look at a term in the denominator. If you look at z squared plus 4, which is in the denominator, by the triangle inequality, that is, the modulus of that is greater than or equal to, I'm just going to write here on this semicircle, the magnitude of z equals r. Because then what I can say is that this is greater than or equal to the magnitude of z squared minus 4. That is the triangle inequality. And the magnitude of z squared is r squared on that semicircular path. So what we in fact have, if we want to try to get a bound on this integral, and in order to use the estimation theorem I will want the magnitude of this, but in fact because of the squared terms in there we can effectively ignore the modulus signs. What we have for this is that this is less than or equal to, and now I'm going to use the estimation theorem, which again you may need to look up if you are unfamiliar with it. But basically you look at the bound, the upper bound of the integrand itself, and the integrand on this contour is always going to be less than or equal to r squared over, and we said that the denominator was greater than or equal to r squared minus 4 all squared. So what I have here is that the integrand is always less than or equal to r squared divided by r squared minus 4 all squared. And by the estimation theorem I have to multiply by the length of the contour that we're integrating over. And that's half of a circle, and so it's half of 2 pi r, it's just pi r. So have a think about that if you're not happy with those steps. Again, you may need to stop the screencast. The estimation theorem, basically, in general, I'll just write it out for you. This is a rough, it's not a full definition, but the estimation theorem says that if the magnitude of a function of z is less than or equal to m, then the magnitude of the integral of f of z around a contour is less than or equal to ml, where L is the length of the contour. And here what we had was that f of z was z squared over z squared plus 4 all squared. So the magnitude of f of z, and again you can drop some of the modulus signs, and then because of the triangle inequality we had that, and then the magnitude of z, as I said, is the same as r on the semicircle. So that's where the estimation theorem result came from, and that's the result in blue here. I'll just write that out again for you down below. This is what we have ended up showing. And I'm just going to multiply through by the pi r. So I have found an upper bound for that second integral, the integral of around gamma 2. And what that means is that when I want to look for the limit of that integral, I can just look at this expression here, the expression on the right hand side, and I hope you can see that I effectively have an r cubed term on the top and an r to the 4 term on the bottom. And so as r tends to infinity, that expression will tend to 0. And therefore the limit as r tends to infinity of that expression is 0. And that means that the contribution to the integral over gamma is in fact 0 from this part of the integral. And what that therefore means is that in the limit as r tends to infinity, I've got that expression there, and that is indeed the pi by 4 that I had before. You may need to scroll back up to check that, but I had pi by 4 as my integral over the whole of gamma. And in this case, that is then the solution to the original problem that was posed.